slides, we do two examples. Okay. All right. The first example, solving a special equation called this Laguerre's equation. Yeah. How special it is? First, let's look at the equation. Yeah. Solve Laguerre's ODE t y double prime plus parenthesis 1 minus t y prime plus ny. So this equation, definitely comes from a special application problem. If you look at the title for this part of E, we want to use Laplace transform to solve variable coefficients. Here you can see we have that variable coefficients, right? Yeah. But if you look at the equation closely, the variable part, t1 minus t, although variable part, but very simple type. Yeah. So, and the reason we can only handle relatively simple variable coefficients because when we apply Laplace transform, we know how to calculate it. Think about if we put relatively hard variable coefficients, then you cannot find Laplace transform. Yeah. So, although from the title, so you can see we may not be able to handle most of the variable coefficients. Here, because t, we know multiplication, we have formula. Yeah. So we have some special formula, so we can calculate. Yeah. T times But think about if we don't have the formula. Yeah. So then it could be very hard. Okay. All right. So let's look at what special formula. So here, first derivative, second derivative, we use these two basic formulas. Okay. Then t multiplication, so we need this formula. Okay. Laplace transform of t times t multiplication derivative at the s side, we need this formula. So then we can calculate Laplace transform of each term containing t. Yeah. All right. Yeah. So let's first apply Laplace transform. Then each term, now we need to calculate each term. Yeah. But the terms containing t, we need to apply this formula. Yeah. First, for the term without that t, we can get an expression easily. Yeah. All right. So now the term with a t, all right, when we apply this formula, little f of t corresponds to y prime. Okay? Little f of t corresponds to that y prime. Okay? All right. So then, this side we should take derivative on Laplace transform of that y prime. This is Laplace transform of y prime. Okay? So we copy this whole expression here, then we take derivative with respect to s. So that's how we apply Laplace transform. All right. Second, for this term similarly, okay, let's look at the Laplace transform of double prime first. Then we factor in that t. Yeah. So double prime, this one, double prime. Yeah. Yeah. All right. That's the calculation. Simple calculation. Okay. All right. Double prime formula. Yeah. Second one there. Yeah. All right. So then, let's do LT times double prime, this time negative derivative, then the brackets containing the whole expression for the Laplace transform of the y double prime. Okay, yeah, all right. So then just take the derivative, product rule, simplification. Yeah, so we have all these expressions. Algebraic computation after that. Yeah. Because after these a few steps, you can see, you know, here we cannot say completely algebraic equation because of capital Y derivative, still differential equation. Yeah. First order differential equation. Yeah. All right. Yeah. So here. Simply, yeah, right. So here, then, yeah, because here we want to add all, you know, yeah, all those terms, okay, all those terms, okay. The first term, second term, yeah, second term, third term, minus, right, minus, so plus, minus becomes minus plus. So here, plus, okay? The fourth term and capital Y. Yeah. So let's add up all these terms and do some simplification. We get this expression. Okay? So what, yeah, dy over y, separable here, separable ODE. Yeah. All right. So we can find a solution easily. Yeah. Here I just write the solution expression. Yeah. Solution expression. Yeah. Yeah. Because you know you have natural log, right? Minus division. So each one, you know, after natural log you take e, right? Yeah. Yeah. So then you have this expression. Okay. All right, so then we need to take inverse Laplace transform. Inverse Laplace transform. Okay, yeah. All right, so here, this little l, yeah, look at the name of the equation, that Laguerre's equation. So the little l represents that, you know, inventor's initial, little l n equals inverse Laplace transform of capital Y. Next, we need to calculate Laplace transform of this expression. If we use the general n number, do you know how to calculate it? We can expand it. Yeah. We can, you know, apply the binomial formula, expand it, you know, term by term, then Laplace inverse transform. Yeah. Yeah, that way we can calculate. Yeah. Although you need to do some computation. Here I give you the answer. I just copy this part. But the answer given containing this nth order derivative on this special function. Yeah. That means if you expand that function and then you also take inverse Laplace transform, you compare, they are the same. Yeah. But that is just a special form, yeah, containing nth order derivative. Yeah. Yeah. Although we can verify, yeah, but here just let you know, yeah, the solution can be calculated. Yeah. Okay, yeah. All right. Yeah, but if I give you lower degree n here, high degree computation a little hard. If I give you, for example, 1, 2, 3, can you calculate inverse Laplace transform? Then that should be easy, right? Yeah, yeah. 1, 2, or 3. Yeah. That's the not too complicated. Yeah. Just, you know, simple practice questions. Yeah. All right. Yeah. So that's that question. Yeah. Then the last example I want to show you, systems of ODEs. Yeah. Yeah. Next, we want to use Laplace transform to solve system of ODEs. Yeah. Then you can see we have another powerful tool to solve systems of ODEs. Yeah. The solution also, I feel, much simpler than our old solution. So you don't need to take eigenvalues, eigenvectors. You can get around eigenvalues, eigenvectors, just the algebraic computation. Although you need to split fractions, that's the part you need to do. The fraction. Split a relatively complicated fraction to, sum of simpler fractions. Then you take Laplace transform. Yeah. So let's look at this example. Our old question type, yeah, mixing problem, this two-tank system. Yeah. This time we use Laplace transform to solve it. Okay. Tank T1 in the figure initially contains 100 gallons of pure water. Okay, yeah. Initial value 0. Yeah. The salt, amount of salt 0. Okay. Tank T2 initially contains 100 gallons of water in which 150 pounds of salt are dissolved. So initial value of y2, little y2 at 0, at t equal to 0, initial is 150 pounds. Yeah. Yeah. So it's a IVP problem. Yeah. The inflow into T1 is 2 gallons per minute. Yeah, here, this one, 2 gallons per minute from T2, and 6 gallons per minute containing 6 pounds of salt from the outside. Yeah. The inflow into T2 is 8 gallons per minute from T1. Okay. Yeah. And, the outflow from T2 is 2 plus 6 gallons. 2 plus 6, 8 gallons per minute. Okay. As in the figure. The mixtures are kept uniform by stirring. Find the salt contents, y1 function, y2 function in T1, T2, respectively. Yeah. 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 So we're familiar with this question. Yeah. Set up 2 equations, 2 ODEs as a linear system. Yeah. So I think you're familiar with how to set up, right? Inflow, outflow. Yeah. Inflow, outflow, right? Yeah. So that's 6. What's that 6? This one. Yeah, that's 6, right? Yeah. Right. That one is pure 6 pounds per minute. Yeah. Here we're setting up equations for the rate, rate of change in 1 minute. Okay, 1 minute. Yeah. So that's the, that one. Then in y2. So, all right. So in out, right? Yeah, out. Okay, out. Yeah. So you need to multiply y1, y2. Question?
Is it saying that there's 6 gallons of water going in per minute? Is it also saying that there are 6 pounds of salt going in?
Yeah, good. All right. Right, correct. 6 gallon per minute water, containing 6 pounds of salt. Yeah, yes, good. Yeah, so here we use salt amount to set up equations. Yeah. So the water amount, mixture amount. Yeah, we use to look at if it's balanced or not. Okay, inflow, outflow, that amount should be the same. Yeah. So So we use gallon number. We see if, because remember we call it balancing, balance law, right? Yeah, balance law. How do you know balance? So we look at it in, number of gallons in, number of gallons out. That should be the same. That number should be the same. So we use, gallon. We check the balance law. Then salt, we set up those equations. Yeah. Two things. Yeah, we use. Yeah. All right. Yeah. Now solution. Now here we do not take eigenvalues, eigenvectors. Okay. Although so that way we still, it's one of our tools in our toolbox, but now we have a new tool. Okay. New powerful tool. Yeah, initial conditions. All right, so now, because we only have first derivative, we don't have second derivative. So we only need to use this Laplace transform for first derivative, not second derivative. Then, let's take Laplace transform. Yeah, here I just copy from the textbook, a little smaller. Yeah. All right, so you can see, for the first one, Laplace transform, you can use here, you use the initial condition, it's gone, okay? Y1 of 0, it's 0, so it's gone. You only have S times capital Y, Y1, capital Y1, okay? So that's the S here, because you move to one side to the other side, okay? All right, so so here, look at that, okay? Negative 0.08 minus, because you move S times Y1, capital Y1, to this side, so you have this coefficient, then plus, minus 6, 1. Laplace transform of 1, okay, so 1 over S. Yeah. But you move to the other side, so negative, okay, yeah. Similarly, you have second equation, yeah. So that's the algebraic equation. This time, so you convert it to linear. Yeah, it's linear. Okay. Yeah, linear algebraic equation. Yeah. All right. We can solve capital Y1. This expression. You need to split. Yeah. So here. Yeah. Here the result splitting that relatively complex fraction. Here, I want to ask you again, when you split this one up, do you feel comfortable? So when you do calculation, splitting this one, do you feel you need to use a lot of time to do the calculation? Setting up, a partial fraction? Think about that. Think about that. Yes. But at this point, do you have a clear idea how? So, if I ask you to do it right now, what do you plan to do?
Yeah, look at my notes.
All right. Okay. Yeah. So let me work a little bit. Yeah, because I did this fraction split a few times, but many students still. I got the feedback still, couldn't follow my way. Yeah. Remember, I remember a long time ago, I talked about split, minus A minus B. Do you still, let me use this, minus A minus B, So here, I remember I also include some formula, because if in the final, if we give you a question like this, I hope you do not spend too much time. When you prepare, try to practice. Do not spend, if you spend half an hour, that's too much, okay? Too much time. So definitely you need to practice to save time. I remember I did one example before, x minus A, x minus B. Split that fraction. Do you still remember how to split? X minus A, x minus B. Oh, yeah, let me use more space here. More space here. X minus A, x minus B. Yeah, I notice some lagging thing. X minus A minus, can you understand this way? First, I just split in this way, forcefully, okay? Although not balanced, right? Definitely not balanced. Can we multiply some constant to make it balanced? 1 over what? A minus B, right? 1 over A minus B. Can you understand this step? This split, basic splitting formula. Can you understand this one? If you can follow, then so you can practice in a relatively fast way to split that 3 product, because this one is 3 product case. S plus a constant, another factor S plus another constant. 3, not that 2. Yeah. But we can use the 2 factor split twice. We can get that twice. Okay, twice. Yeah. All right. Yeah. Yeah. So here, I don't know. So yeah, if you, how hard you feel, do the splitting. Yeah. Yeah. If you try your way, look at how much time you need. Okay. Look at. So I hope you can control within 10 minutes. If you can solve question like, if you can control within 10 minutes before the final. Think about that.
Question.
Mm-hmm.
So if the beginning equation was x plus A, x plus B, how does that affect the end equation? Which minus signs then become pluses?
Oh, good question. Yeah. Yeah. All right. Now let me change plus version. Good. Yeah. All right. Plus version. All right. Now, common denominator, numerator x plus b minus x plus a, x cancel out, b minus a. So we put a b minus a here. B minus A to make it balanced. How about that? Yeah, good. Yeah, Andrew's suggestion good. You have 2 versions, plus version, minus version. Because sometimes you see plus, yeah, whatever, yeah, but you can adjust plus, minus. Yeah, good. All right. Yeah, because here common denominator, then the numerator x plus b, numerator x plus a. Take difference, x cancel out, b minus a. So you divide b minus a to make numerator 1. Yeah. Good. Yeah. Try to feel comfortable to do split like this. Okay. Then apply it twice. Apply that formula twice. But twice, the first time is tricky. Yeah, here, I want to let you know, the first time is tricky, okay? I want to show you the first time. First time. Yeah. If I do not tell you first time, it's very hard for you. So I show you the first time split. Second time, we use this formula, okay? Second time, each one, 2-factor product, denominator, yeah. Yeah, but I notice significant lagging. Did you notice that when I writing lagging? So the solution, yeah, Remember I did last time. I need to shut down, turn off the cloud computing. Yeah. So that cloud computing causing problem. All right. So OneDrive. It's called a OneDrive. OneDrive, yeah. That's the cloud computing. Yeah. Yeah. Oh, yeah, it looks like. All right, yeah. So here I need to turn off, okay? Pause. Quit OneDrive. Okay, quit OneDrive. All right. Now let me see if my writing is faster. All right. All right. Now I show you the splitting. Yeah. Let me use the space here. I just show you the idea. Okay. Use the little space here. Show you the idea. All right. The thing is at the denominator. The hard part is at the denominator. Okay. All right. Yeah. All right. Let me change the pen color. Okay, all right. Yeah, look at the trick here. Okay, all right. S times S plus 0.12, S plus 0.04. All right. Look at what two fractions do I use? S times S plus 0.12 minus S plus 0.12 times S plus 0.04. Look at this way. How about that? Not balanced, let us multiply appropriate constant to make it balanced. Can you see what constant, special constant we should multiply to make it balanced? Can you see that? Constant, no S. What constant? We put at this place to make it balanced. Can you see that? Common denominator. What's the common denominator? Look at the common denominator. Okay? Oh, sorry. Common. Oh, yeah. Yeah. Look at the common denominator. This factor common, right? This factor common. All right? This here. Numerator, you need to multiply S plus 0.04, right? Yeah. Here, multiply S, right? S plus 0.04 minus S. What's that? Yeah. 0.04, right? So let's put a 0.04 here to make it balanced. Can you see? Yeah. This first step split. Yeah, like that. Second step, now you can apply the formula, right? That one. Yeah, because two factors. Two factors. Okay? The second, each one you can apply that formula. Okay? But the first step, you do this way. Yeah. Think about, so this is one. So the way I use, I feel comfortable. So here you have two ways. Yeah, let's say you have two ways, this way and your old way. Old way, I just say partial fraction. Okay, I just assume your old way is partial fraction. Okay, so you compare which one you can do faster. Yeah. So in the final, so which one you can do, you can, at least you can do within 10 minutes. Yeah, let's say. Yeah. Assume I give you one such question. Yeah, I only need to give you one such question. Yeah. All right. Yeah. Just practice. Okay. All right. Yeah. Let's continue. Yeah. All right. Yeah. Actually, we pretty much. Yeah. So after that, then to get a solution, inverse Laplace transform. Yeah. You just write. Use the formula. Okay. Yeah. Here I keep that. I do not erase. So you can still have my formula for your reference. All right. Now, so we finish part E and we finish module 4, Laplace transform. Now, another thing, at this point, I may update our final question types I said before. Yeah. Now I may like to update because I look at the final question types and also look at the time we left. So we have to change a little bit. So 8 questions in final. First two power series, solving ODE 2. Then Laplace transform. Now I want to add 4. Okay, 4 out of 8 Laplace transform. Fourier transform 2. Okay, then no linear algebra. I said I may like to talk about linear algebra, but I look at the content. Linear algebra, basically similar to what we did. Yeah. So if I go further, that may take too much time. Okay. If I go deeper, then it will take too much time. So the linear algebra, so I may not go there anymore. Okay. So then we move the one question from that linear algebra part to Laplace transform. Okay. Yeah. So that's the update. Yeah. Power series to Laplace transform for Fourier transform 2. Yeah. Also 2. Yeah. 2, 4, 2. Yeah. Yeah. All right. Okay, so let's go to module 5, Fourier analysis. Yeah, actually this chapter 5, module 5, I feel very important. Yeah. So probably the remaining of the semester before final review, we need to do some review. Before that, I like to spend all our time on this module. Yeah, because based on your knowledge part, so you need some, important knowledge, Fourier transform and Fourier analysis. Yeah, there are several topics. Yeah, I can only pick half of the topics. Yeah, but that half of the topics are very important. Yeah. So I like you to know, the basic ideas. We don't have a lot of time to practice, but I like to give you, introduction. Yeah. And another thing is, last time I said we cut one homework assignment, right? Yeah. We only have 3, not 4. Yeah. We also cut one quiz. We have total 5, not 6. Okay, 5, not 6. And this weekend we need to do number 4. Okay, number 4 is for module 4. Number 5 is our last one. We still do similar to our midterm. The last quiz, that's the first 10 questions of final. Yeah, just like the midterm. Yeah, the concept questions. Yeah. Yeah. So then our, oh, not 10. 9, yes, good, yeah. So 9 plus 8, yeah. In classroom, we do 8, yeah. 9 plus 8, yeah, all right. Okay, yeah, so that's the updates. All right, yeah. Module, yeah, I haven't uploaded, yeah. All right. Yeah, introduction. Yeah, today, the first one, introduction. Yeah, because the reason this part is important related to signal processing, image processing, the later part. Yeah, but we need to prepare 1 or 2 lectures. Prepare, then we can go to image processing, signal processing related transforms, Fourier transforms. Yeah. Oh, yeah. Question. From Ian, yeah. Let me look at the chat question from Ian. Yeah. Now we have one less quiz. Yeah, and yeah. All right, the weight. Yeah, you're right. We scale. All right. Yeah. So don't worry, because one less, yeah, and I scale a little bit. Okay. Yeah. I remember I did like this. For example. When we have 4 homework assignment, each homework 10%. Now 3, each one 12%. 3 times 12, 36. There, I just adjust, okay? Midterm, add 2 points, right? Final, things like that. Or, quiz, add 1, or scale up, okay? Yeah. Another way is I do not adjust. I still use our old weight. But at the end, I scale to 100. How about that? At the end, because we miss 10% from homework, 4% from quiz. So it's 86% total. 86, I just divided by 0.86. I scale it to 100%. How about that? Right? That's a simple way. We do not change anything. Okay? The last step, we just scale it. Stretch to 100. Stretch from 86 to 100. How about that? That's the easiest. Okay? That's a fair way. Yeah? Yeah? Okay? Yeah.
Were you still planning on dropping the lowest quiz grade? Or?
Yeah, I still planning dropping lowest. Yeah. Yeah. All right. Yes. 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 All right. Yeah. Yeah. Now, this last module, very important. Yeah. So that's, yeah. Top title: Fourier analysis and a partial differential equation. Yeah. Partial. Yeah. I may. Yeah. Yeah. Most of our time I use on Fourier analysis. Partial, I may just use, for example, the last lecture, second half, just give you some basic idea introduction and a few simple example. Yeah, so let you see, some simple idea. Yeah, partial. Yeah. It's important, but we do not have that much time. Yeah, so yeah, so I just show you. 1/2 of the lecture about partial differential equation. Yeah. Part A, Introduction to Fourier Analysis. Yeah. 8.1, Introduction to Fourier Series. Yeah. So, all right. New interesting topic. Okay. All right. First, we need to consider periodic. Yeah. We should say periodic function. Yeah. Functions with period. Okay. Periodic functions. Yeah. All right. Yeah. Then, first we need to look at the, why we want to study periodic functions. Yeah. Model periodic phenomena. Yeah. In the real world, if you just pay attention, you can see large number of phenomena related to period property. Period property. Okay. Rotating parts of machines. Yeah. So rotating. Alternating electric currents. Yeah. Alternating. Okay. Yeah. So DC AC, right? Yeah. That AC. Yeah. All right. Or the motion of planets. Yeah. Planets. Okay. Sun, Earth. Yeah. Period. Yeah. So you can see so many periodic phenomena. So definitely we need to find a better model for it. Yeah. Our current, we do not have our current methods. We do not have a good model for it. Yeah. Good model for periodic functions. Yeah. All right. So we have to use periodic functions to model. Yeah. So you cannot use power series. Power series is not a good model. Okay? Power series, no period. Okay, power series. Yeah. All right. Question: how to represent so many different types of periodic functions? Yeah. Because periodic, it could be, very different. Yeah. So we have to use one special way to model periodic functions. Yeah. Answer: use simple and flexible periodic functions. Yeah. Cosine and sines. Cosine and sines. Yeah. Yeah. Any periodic function, we use cosine and sine to model. Here you can see another level of model. You can see here two levels of modeling. Okay, the first level, real world application problem, we want to model periodic phenomena. So that's one level. Okay, yeah. But the real world periodic phenomena, you have periodic function modeling functions. But those periodic modeling functions, you need another fundamental periodic functions to model. Okay? Because those general periodic functions not fundamental, right? So they are arbitrary periodic functions, but they are not fundamental periodic functions. So we want to use fundamental periodic functions to model arbitrary periodic functions. And these two functions we treat as fundamental periodic functions. Yeah, yeah. Foundation, okay? Yeah, building blocks, foundations for general periodic functions. Yeah, very powerful. Yeah. And this invention, Fourier analysis invention, that's another big revolution in mathematics. Yeah. Another, yeah. All right, so let's look at the definition of periodic function. A function f of x is called periodic function if f of x is defined for all real x except possibly at some points. Yeah. So here you can later we will see why we always say except possibly at some points. Yeah. Because if at a certain number, finite number of points, if the function is not continuous breaking points, then this theory works well. Okay, this this theory allows those finite number exceptional discontinuity points still works well, okay? But must be finite many, okay? If you know, too radical, you know, too bad, okay? Yeah. So this is tell you the worst it can handle. Yeah. It allows finite many bad points, okay? Bad points, yeah. But not too many, okay? Too many bad points, then the theory breaks, okay? All right. And if there is some positive number p, p refers to period, okay? The period of the function, positive number p, called a period of f of x such that, yeah, what do you mean period? Yeah, so this identity, yeah, so we treat, yeah, for this function, always true, everywhere, for all x. For all x that f of x is defined, yeah, because some points f of x may not be defined. Yeah. Later you will see a few points, the breaking points. Yeah. The function not defined. Okay? So we do not consider those points. Undefined points. So for all points in the domain, yeah, in the domain, we have this formula. Okay? All right. Yeah. Observation. Yeah. Because if this equality is true, can we say x plus multiple n multiple, no? Any integer n multiple that p, also true, right? Yeah, because we just apply that period property a few times, n times, okay? Yeah, so we also have that, yeah. Then, because based on this observation, when we define a period, we should not use this. When we define, so here we want to use the smallest p to define it as we call the fundamental period. Yeah, because that's smallest. Yeah, we don't want to use n times p. Yeah, so we want, you know, single p, 1p. So smallest p to make this true, that's the fundamental period. Okay? Smallest positive period. Yeah. All right. So after that, then let's study the basic properties of periodic functions. First, trigonometric series. Trigonometric series. Yeah. Yeah. We use sine, cosine. Okay? Sine, cosine. Yeah. Yeah. Unknown coefficients, A0, A1, unknown coefficients. Yeah. So, yeah. This form we call trigonometric series. Yeah. All right? Yeah. The first. That trigonometric series, then you have the convergence issue, right? Yeah. When you have an infinite series, there is a convergence question. Okay? All right. So here we consider trigonometric system. 1 cosine x, cosine, you know, all these basic functions, yeah, sine, you know, and nx, cosine nx, sine nx. Put all of them together, and we form a trigonometric system. It's a form a system. So what's that system? Yeah, the system. Yeah, we used the basis concept before, right? Yeah. So actually, this system forms a basis for certain function space. Yeah, but that probably too abstract. So we do not go too far. Yeah. So that's why our textbook does not mention the basis concept here. Yeah. So here we, you know, for you, because basis concept, you know a little bit. Yeah. So you just know this system forms a basis. Yeah. Basis means you can represent, you know, everything in that function space. But that function space, you do not know. Yeah, so that's the reason. I do not talk about that too much. Yeah. All right. Convergence of trigonometric series. Convergence issue, very important, but for us, we don't want to spend much time on convergence. Yeah. We just assume when the functions are good enough, not too bad, so then we have the convergence. Okay? We assume we have the convergence. If it's bad, then we may not have the convergence. Yeah. All right. So the trigonometric system is orthogonal. Another important property, orthogonal. The basis, yeah, because these are the basis functions. Orthogonal, we talk about these basis functions are orthogonal. Okay. Right, perpendicular, Pythagorean theorem, orthogonal, 2D, orthogonal. Yeah, but here it's not 2D, it's an infinite dimension. Yeah. Each basis function has one dimension. Okay, how many dimensions? Infinite many dimensions. Yeah. So that function space has infinite many dimensions. Yeah. All right. So orthogonality means when m not equal to n, integers to integers, all right, you take product of any two different basis functions in the system, you do integration over one period. Yeah, because this from 0 to 2 pi, that's one period. Okay, it equals 0. Yeah. But here, we even allow n and m the same, because cosine, sine are different. Even when n and m the same, sine, cosine, they are different functions. So when the basis functions are different, then the product of the integral equals 0. That's the orthogonality. Okay, orthogonal. All right, yeah, because this integral, something like projection. Projection concept, right? Projection. Where perpendicular, two lines perpendicular, the projection equal to 0, right? Yeah. Vertical line, projection on the horizontal line, the length of the projection is 0, right? Yeah. So this integral like the length of the projection. Projection is 0. So perpendicular, okay? Yeah. All right. Cosine, the same function. This time we require n and m different. Yeah. Same function, then the n and m must be different. Otherwise, the same function, square, it cannot be 0. Okay? Yeah. Different, orthogonal, perpendicular. Okay? All right. Yeah. Similarly, for sine, we also have m and n different, orthogonal. Okay? Yeah. So these properties very useful when we do the Fourier expansion. While we have the formula for Fourier expansions, we need to use these formulas. Okay? All right. These functions are linearly independent. Yeah, definitely. Orthogonal. All orthogonal basis functions must be linearly independent. Yeah, orthogonal. Okay? So that's the strong property of orthogonality. Okay? Yeah. Linearly independent. Yeah. Yeah. Suppose you have certain number of basis functions. If you know they are orthogonal each other, okay? Orthogonal each other, then they must be linearly independent. That's simple. Yeah. You can prove easily. Use the definition of linear independence. C1, adding all those. Then you use orthogonality to show all C are zeros. Orthogonality, you can show all C's are zeros. That's simple. Okay? All right. Yeah. All right. Yeah. So here, question. Yeah, let me put a question here, then we take a break. Okay. Can we represent any 2 pi periodic function in a trigonometric series? This question, the answer of this question That's the foundation of the Fourier analysis. Yeah. Fourier, yeah. So this, French mathematician, yeah, invented this whole theory, and he's submitted his work for publishing, but got rejected. Yeah, because those mathematicians couldn't understand. So ridiculous. So I mean, you are doing garbage. Okay, we couldn't understand, but so valuable, extremely valuable for your analysis. Yeah. All right. Yeah. Take a break. Yeah.